Hello, how are you doing? It's Mike here, and in this video we're going to talk about polar coordinates. And depending upon what class or maybe where you are science in your science path or your science career, you may have seen polar coordinates. You may be working on them in a couple different venues. You can see them in pre-calculus, and you can see them in trig, you can see them in calculus. So you're going to see polar coordinates everywhere. So, when I think about graphs, I think of three different types of graphs. I think of traditional functions, I think of parametric curves, and I think of polar curves. So let's go ahead here and let's define our polar coordinate system. Our polar coordinate system. So then nothing here is really that advanced. This is just going to be nomenclature. So let's go ahead and say that we have a plane, and I'm just going to use this example over here. I know it's slightly bright, so hopefully it's not too offensive to your eyes. Notice here that we have angles. We have angles, and then we also have different circles, and these circles all have a radius. So these radius could be any radii value that you want. 1, 2, 3, 4, 5. So this could be a 1. This could be a 2, this could be a 3, this could be a 4, this could be a 5. If you wanted to make it values of 2 or 5 or 10 and increments thereof, you could do that as well. And then our angles here are in 30 degrees, so we could also say this is pi over 6, and this could be pi over 3, and then we could have pi over 2, and so forth. So for us, it doesn't really make a difference on how we label that. I tend to work in radians, but I really like this graph a lot. So it's very simple to use, and it's very clean, and it's not too pixelated, so I really enjoy using this. So we'll say there's going to be a fixed point, so there's going to be a fixed point O, and we'll call this fixed point O. So that value of O can be anywhere. That value of O can be anywhere, but we are going to say that the point O is going to be at the origin. So for us, we're going to make it really easy, and this is going to be a value of O. So that's going to be right here at the origin where I just colored in. And this is going to be called the pole, and it's also known as the origin. So I know that when I was growing up, that my teacher in high school used to say, well, Santa's from the North Pole, so that's the origin. Sometimes people would, I don't know, maybe help me remember where it was. So even if you don't believe in Santa, it's your discretion how you want to memorize it. But instead of calling the origin, we often refer in terms of polar coordinates or a polar plane as the origin being known as the pole. So just keep that in mind as we're working through it. The next thing we're going to discuss is the polar axis, and I'm going to highlight for you. I'm going to highlight our polar axis. So the polar axis is going to be, well, maybe I'll do it in red. So it's going to be this guy. So this is going to be our polar axis right here. So that's going to be our polar axis. Let me just write polar axis. So we can read that. It's really bad handwriting, I'm sorry. So let me try one more time. I really have to make this better. Polar axis. So that's going to be our polar axis. And the next time we're just going to have to define a point P. So I'm just going to pick a point P. I'm going to call this point P, and I'm going to say this point P exists right here. So as we see, it runs along this this radial axis, and I'm just going to go ahead and draw a ray. I'm going to draw a ray from the pole to my point P. So I'm going to draw a ray from the pole to my point P, and we're going to define this point P in terms of a polar coordinate, and we're going to say this value is r comma theta. So this is very different than what we've done before. So r for us is going to be equal to the radius. And I know this seems a little interesting, but when I say radius, each one of these circles, as we see, has a consistent radius. So as I've named them earlier here, 1, 2, 3, and 4, we often, say radius, but I don't think that's the proper nomenclature for a value of r. We often will say that this value is going to be the distance from the pole. We should actually formally call it the distance from the pole to the point P. So it doesn't have to be an integer value. It could be a rational value, but for what we're going to do right now in this video, we're going to keep it relatively nice. So for us, as you can see here, that we have gone out 1 value of the radius, 2 radii, 3 radii, and 4 radii. And that means that our value of r for us in this example is going to be a value of 4. And we have the ray, so I'll just write this out formally. The ray is equal to OP. So that works out really nice for us. So the value of r is the radius. Sometimes this is often referred to as, I'm just going to write this down here, as the radial coordinate. And the value of theta, that's going to be the next portion we're going to discuss. We're going to have to discuss this value of theta. So that's my horrible theta. Let me try redrawing theta a little bit more like theta. So theta, okay, a little bit better. So the value of theta is going to be the angle between the polar axis and the ray OP. So this is going to be my angle of theta. And theta is often known as the angular coordinate. So this is known as the angular coordinate. It's also known as the polar angle. Just if you ever hear the word angle, and you're discussing a polar plane, think it's going to be the angle created between your ray and your polar axis. So there's just a lot of different nomenclature here. We're not really doing a lot of math. We're just sort of naming all of these points. So we're coming up with a conventional name. We're coming up with a conventional name for all of these points. So what I like to do is that I like to go ahead and maybe graph some points, graph some polar points, and we'll see what they look like. So notice here, let's go ahead and look at this. I'll do a couple of them. I should have this already done. Okay, so let's go ahead and graph our first point. So let's look at maybe let's look at 4 and pi over 4. And this is going to be our first point that we want to graph. It's going to be 4 comma pi over 4. So pi over 4 is approximately 45 degrees. So that's going to be approximately right here. And so I'm just going to draw this in with maybe a dotted line. But I want to go out a radial length or a radial coordinate of a value of 4. So for me, I'm going to look at 1. This is going to be 1 circle. This is going to be 2 circles, 3 circles, and 4 circles. So I recognize here that this is going to be my value of 4 comma pi over 4. So this is going to be my point 4 comma pi over 4. So I'm just going to clean this up just to make this look a little bit better so we don't have any confusion on where this point is. But that's how I come up with it in my head is I count out the amount of circles. And the nice thing about these polar coordinates is that they're going to be consistent. So this is just the point 4 comma pi over 4. 4 comma pi over 4. So be cognizant about that this is the point 4 comma pi over 4. So let's look at another one. Let's look at a point. Let's see, we've got 1, 2. Let's look at over here. Let's look at 5 comma 2 pi's over 3. 2 pi's over 3. So we have to think to ourselves, okay, oops, let me close my parentheses. So I want to go out a value of 1, 2, 3, 4, 5 circles. So I know that I'm going to be working somewhere, let me highlight instead of doing this, somewhere here. So this is the 5th circle that extends from the pole. But now we have to figure out, where does 2 pi over 3 exist? Where does 2 pi over 3 exist? So hopefully we're able to rapidly interconvert between radians, and for us, since this polar paper, these polar graphs are in terms of degrees, that we have to be able to rapidly convert between radians and degrees. But if you forgot, it's okay. Remember that pi is equal to 180 degrees. So everywhere you see pi, all you do is plug in 180. So if we want to figure out 2 pi's over 3 are, this is going to be 2 times 180 all over 3. Notice the 3 and the 18 cancel, so 60 times 2 gives me a value of 120 degrees. So we recognize it'll be working here. This is going to be our point, 5 comma 2 pi's over 3. 5 comma 2 pi's over 3. So we're actually going to be transcending from here all the way over to here. So that's going to be our angle 2 pi over 3. 2 pi over 3. So let's try a couple more. We'll look in the third and the fourth quadrant just to make sure that we feel very comfortable. Graphing these. Okay, so we got another one down here. Another one down here. So I'm going to just throw out some points for you, and I'll let you take a couple seconds to figure them out. How about graph 3 and 5 pi over 4? So let's graph that polar point. And then how about 4 and 11 pi's over 6? So if you want to, you can pause the video and try plotting these points for yourself just to make sure that you understand how to get them. Okay, so let's look at this first point. Let's look at this first point, 3 comma 5 pi over 4. So I know that I'll be working 1, 2, 3, a distance of 3 something out. So I'm just going to call this 3 circles. So I recognize that my point is going to fall somewhere along this highlighted region, and I need to go 5 pi over 4. So the way that it helps me, if I just can't rapidly interconvert, I know that 4 pi over 4 is equal to one value of pi, and here is my value of pi, 180 degrees. Remember, this is equal to 180 degrees. So if you have a problem, rapidly converting, it's okay. It's not uncommon. But now if we think that we're going 5 pi over 4, that's going to be 4 pi's over 4 plus another pi's over 4. 4 pi's over 4 plus another pi over 4. So we're going to go 180 degrees plus another 45 degrees. So we're going to go all the way from here, from our polar axis, all the way down to here. So all the way down to here. So this is going to be our point 3 comma 5 pi's over 4. So we're traveling pi plus another value of pi over 4. So this value here, I'll just do it in green. This value here from here to here is going to be a value of pi over 4, and this value here is 4 pi's over 4. So from the coordinate, the polar axis to pi, 4 pi's over 4, then you add another pi over 4. That's how I do it. So then, you come over to the next point here. So we're working along the 1, 2, 3, 4 circle. So I'm going to go ahead and just highlight here along my 4th circle. So I know my point will fall somewhere here. I'm going 11 pi over 6. So I know that 2 pi revolutions is going to be one full transition, we're traveling the circle one full revolution. So 2 pi is equal to 12 pi over 6. 12 divided by 6 gives you a value of 2. We didn't travel a full 12 pi over 6. We've only traveled 11 pi's over 6. So I know 11 pi's over 6 plus another pi over 6 would give me 12 pi's over 6. So I recognize that I have to go down 1 pi over 6. So I recognize that 11 pi over 6 is the same thing as saying negative pi over 6. 11 pi's over 6 is the same as saying negative pi over 6. And you can't have negative polar angles. So we can travel negative 11 pi over 6, or we could travel 11 pi's over 6. And we want to go out to a radius 4, so this is going to be my point there, 4 comma 11 pi's over 6. That's a horrible notation. Need a little more writing room. So we're going to have 4 comma 11 pi's over 6. So that's just a quick summary of how to plot points and how to work with your different polar axes. If you are in Calculus 2, then this should be a review for you. If you're working in pre-calculus or trig, this might be relatively new, but it just takes some practice, making sure you can interconvert between radians and degrees, and how we're working with different axes.